we will continue from where we left last time. And the last thing that we discussed was how to calculate the percentage mass of an element from the formula mass, right? We solved a few questions from the end of chapter questions, and I did this question, I remember. So after that, and then in the same with the same method, we can also calculate the percentage of mass of crystallization in hydrated salts, right? And today we are going to do this page 155, and in which I will discuss this experiment. How experimentally can we find the formula of a compound? Okay, how can we by experiment calculate the formula of a compound? Now the basic theory behind this experiment is that since every compound has a formula, and formula is, what is a formula? What is a formula? Okay, the chat option is disabled. Okay, the chat option is disabled. So we will work on that. Inshallah, it will soon be enabled. But for now, the chat option is disabled. Okay, formula represents the number of atoms of each element in a compound, right? And this experiment is going to prove that whatever the elements are present in a compound, they are present in a fixed ratio. Their masses are in a fixed ratio, and their number of atoms are in a fixed ratio. Now, because the number of atoms of each element is in a fixed ratio, therefore the masses of the elements will also be in a fixed ratio. So we are going to prove that with the help of this experiment. Now, in this experiment, the compound we are going to study, the formula of which we are going to study, is magnesium oxide. The compound would be magnesium oxide. And the reaction will be magnesium. Can you please hold this? So the reaction would be this: magnesium reacting with oxygen to give magnesium oxide. This is going to be the reaction. Okay. Oxygen will be provided from the air. Okay. And magnesium is what we will use. We will use a magnesium ribbon. We will use a magnesium ribbon, and this oxygen will come from the air, and this will require heating. Seems like this is an endothermic reaction because it requires a lot of heat. So we will need to heat strongly, and our product would be magnesium oxide. Okay. And we have to find out how many atoms of magnesium and how many atoms of oxygen, right? And what is the ratio of mass of magnesium and oxygen in this compound? Okay, so let's get started with the magnesium. Okay, and we also should know the masses of each one of them. We should know the masses of each one of them, like what mass of magnesium mass, for example, and what we cannot measure the mass of oxygen, but we can measure the mass of the product, mass of magnesium oxide, right? And the difference between the two can give us the mass of oxygen, right? Because remember, there's a law of conservation of mass. The mass of the product should be the sum of the masses of the reactants. I mean, no third thing, no other thing will be added, right, into this product. The reactants should be added up to give the mass of the product. So because we cannot measure the mass of oxygen because it's coming from the air, but we can measure the mass of magnesium, we can measure the mass of the product, the difference between the two can give us the mass of oxygen. Okay. Now, how to measure the mass of magnesium? What is, in chemistry, what is the best way of measuring the mass of any substance? Samdos? We take tare, right? Tare, remember I talked about tare. What is tare? Tare is that we will, first of all, here in this experiment, we are using a crucible. Okay, we are using a crucible, and we will weigh this crucible along with the lead when it is empty first. We will note down the reading, mass of empty crucible plus the lead. Okay, then we will add magnesium ribbon into it and then weigh it again. Mass of crucible plus lead plus the magnesium is this. And then the difference between the two will give us the mass of magnesium, right? Now, my question is, why can't we weigh magnesium directly on a weighing balance? Why do we go this way? Why do we do it this way? Why do we do it the indirect way, the tare? Any guesses? Yeah, I'm sorry I cannot get you into discussion with me because of this. Yeah, Sandus, you wanna give some? No? Okay. Okay, Amna, you raised your hand? Okay. Yes, Amna?
Because magnesium ribbon will be too light to be measured on a weight machine, so that's why we are using this way.
Okay, can you think of any other reason?
Mm.
Can you think of any other reason?
I don't know.
Okay, so that was a good one. Because it's too small, so the precision of its weight on the weighing balance might not be that great. And yes, if we added to the weight of crucible and lead, it would be easier. Secondly, we don't want the weighing balance to be damaged by the chemicals. If in this case we have magnesium, but we might have some harmful chemicals. Secondly, okay, Yusra, you raised your hand. Yes. Yes, Yusra.
Miss,
Yes.
because if we measure magnesium directly, it might show various weight because the oxygen might also combine with magnesium. The more the oxygen, the more the weight will show.
Well, will magnesium react with oxygen at room temperature? No, I don't think so. It's an endothermic reaction. It needs heating. So the reaction is not spontaneous. But yes, that's a good thinking process. I like it. Yes, for those substances that do react under room temperature, this would not be a good idea to expose them to the oxygen in the air. Good job, Yusra. Okay, Zainab Wasim. Yes, Zainab?
Miss,
Yes?
if we were using any other reactive material instead of magnesium, it may react with the balance, and if we're measuring something else, then it would give
Right.
an effect. So it's not good to, just because it's not reactive, doesn't mean it will not affect it. Like it may not affect other things.
Right, right. So I want you to appreciate that why is weighing directly bad is not a good idea. Also, many of the substances are in powder form or are in liquid form. So we cannot weigh them directly. We have to have a container, right? And they also might get damaged by the air and everything, by exposure to air. So yeah, all of those answers are good. Okay, so you should know why we are doing this the indirect way. Now, as I told you, we cannot measure the mass of oxygen, right? So, but we can measure the mass of the product. So the next weighing we will do at the end of the reaction would be mass of crucible plus lead plus magnesium oxide, right? And the difference between these two values will give us the mass of oxygen. Okay, because the only difference between them is the addition of oxygen, right? Okay, now let's talk about the different steps of this experiment. So first, we will weigh the crucible and the lead, and after we have done that, we will add magnesium, and then again we will weigh it, and then we will start heating. And the heating has to be strong. Okay, the crucible is then heated strongly, and keep the lid keep the lid tightly on the crucible. Why? Because we don't want any magnesium powder to be splurting out of the out of the crucible. We don't want that happening. Okay, we don't want any magnesium, burning and turning into smoke and losing mass, right? Because mass is what we are measuring here. And with the help of the ratio of mass, we are going to find out the formula. So we don't want any mass of magnesium to be lost. We want all of that measured mass of magnesium to participate in the reaction. Only then our results would be accurate. Because if the mass is lost, then our calculations are invalid, because not all the magnesium participated in the reaction. Much of it got wasted, right? We don't want that happening. Therefore, the lid should be on. And you will keep an eye on the lid as well. I mean, there should be no powder on the lid. No powder of magnesium stuck to the lid. We want all the magnesium to be burning and reacting with oxygen, okay, under the influence of the flame. And so once you see that the whole of magnesium has burned, okay, then towards the latter part of the experiment, you can remove the lid and then heat it strongly. Why? Because now all the magnesium has been converted into magnesium oxide, and you're just making sure that the reaction has been completed. So now there is no danger of magnesium powder getting splurted out. And remember, magnesium is in the solid form, but it can easily be converted into powder. Okay. See, solid must not be allowed to escape as a white smoke. After a while, the lid may be taken off and the open crucible then heated strongly. The crucible and products are then allowed to cool before reweighing. Why do we cool before reweighing? Why do we cool before reweighing? Can we weigh while the crucible is still hot? Sandus? Yes. Okay. Okay. Zainab. Okay. Yes.
Miss, if it's hot, how would we lift it and put it like where we have to measure it? It would be difficult.
Yeah, first of all, it would be hard to hold it, right? But if, for example, somehow we manage to hold it with the help of something, can we use a hot crucible? Can we weigh a hot crucible on a weighing balance? Okay, let Muhammad Abdul Rahman. Yes?
Yes, ma'am. The vapors will not count. The weight of the vapors will not count.
The weight of the vapor will not, oh, you mean to say that the vapors will be lost?
Yes,
Okay, now, yeah, there's only magnesium oxide in here, no water here. So no vapors. But yes, that's a good thinking. If there was water involved, you could say that. Okay, Ammaz or Rahman. Yes, Ammaz or Rahman. No. Okay, Atika. Yes, Atika. Okay,
The mass,
okay, yeah, go ahead.
the mass or the weight may differ when it's heated highly. The mass
Yes,
of
yes, you are right. Yes. The buoyancy of the vapors, you know, there are no vapors, but there might be some fumes. The buoyancy does affect, and if there are vapors, if there's any reaction where you are having vapors being formed, then yes, you will have that buoyancy effect will decrease the weight, and therefore we should wait for the apparatus to cool down before we can weigh. Also, extremely hot crucible can damage the weighing balance. Okay, extremely hot apparatus can damage the weighing balance, and therefore it is advisable to wait for the things to cool down before you can weigh again. Okay, now for how long should we keep heating and when should we stop? How would we know when we should stop heating? Yes. How to know when to stop heating? Okay, Muhammad Abdul Rahman. Yes.
Ma'am, when this all is burnt.
Okay, when this all is burned. And how will you decide that that everything has burned?
We cannot see the magnesium ribbon.
Okay, no. You have to have some more precise criteria, some more reliable criteria. Yes. Okay, Syed Nabil, you want to answer? Yes.
Miss, when vapors start to vaporize.
No. How do we know that a reaction has completed? Yes, Amna. Oh, sorry. Oh my God, what have I done? Okay, I don't know what have I done. Sorry. Wait, Amna. Where are you? Okay. Yes, Amna.
Because we'll open the lid after some time. If the magnesium ribbon has lost its shine, so we can know that oxygen has reacted with it.
No, that's not a reliable criteria. See, we have to make sure that the reaction has completed. We cannot stop heating till the reaction has completed. So how would we know that the reaction has completed? Study tip. Reweigh until there is no further change in mass. Until there is no further change in mass. So yes, first you will follow the appearance, as you just said, when you can see no more unburnt magnesium left, then wait for it to cool and you can weigh it, and then note down the weight, and then wait, and then heat again for quite a while, and then, let's say for example 5 minutes, and then weigh it again, and as soon as you start seeing the same readings for the weight of the crucible plus the magnesium oxide, that's when you know that the reaction has been completed. Why is it that the mass stops increasing when the reaction is complete? Why is it that the mass stops increasing of the product? Basically, at the end of the reaction, what are we weighing? We are weighing the crucible. We are weighing the crucible with magnesium oxide, right? This is magnesium oxide. So at the end of the reaction, this product we get at the end of the reaction. So why is it that we wait for the mass to get constant? And how does it represent that the reaction has completed? Because yes. Okay, Muhammad Abdul Rahman, yes.
Ma'am, I have a question that how can we wait when it's very hot?
Yeah, that's what I'm saying. You have to wait. You have to wait for it to at least not normalize to some extent. Okay.
Ma'am, लेकिन हम heating को stop कैसे करेंगे?
Remove the crucible from the burner and keep it aside.
Every time removing and keeping like this.
Yeah, with the help of a tong, you can use a tong and then remove it. You know what? I had a video showing you this experiment, but I did not save it because I thought that you don't need a video for this. But okay, I will send you the link in the group if you're interested. Yeah, you can
Yes.
look at the video how he's doing it, how it's shown in the video. So it's not a big deal. He's using a tong simply, and then he's removing, okay, and then keeping it on the weighing balance, and then until he starts getting 3 similar values. When he's getting 3 similar values, meaning that the mass has stopped increasing, he knows that the reaction is complete, and so he stops heating, right?
Yes. Thank you, ma'am.
Yeah, you're most welcome. So, okay, I'll share the link in the group. Okay. So, so why? My question is still there. Okay, Amna, you want to answer? Yes.
Yeah, because no more oxygen will be reacting with the magnesium.
Why?
Because because of the concentration.
concentration, what?
Like the surface area of magnesium is covered all with oxygen, so there's no more space for more oxygen to bond with magnesium.
Okay. Okay. Amra Javed. Yes. Yes.
Yes, we can also plot a graph to show how the reaction comes to a stop with the time and the weight. So you can see the graph is going up and eventually it'll come to a stop. When it comes to that stop, you'll see that it's constant all the way, and then you'll know that the reaction has stopped.
So that's what my question is. Why does it stop? Why does it stop? That's my question. That, you know, why does the graph flat out? Okay. Okay, let me answer that question. Okay. So you had a fixed mass of magnesium, right? You weighed magnesium, right? You have a fixed mass of magnesium. Now oxygen is from the air. Oxygen supply is not ending. It's from the air, unlimited supply of oxygen, right? But when all the magnesium has reacted, there is no more magnesium left. There is no more magnesium left. So though there might be oxygen supply from the air and you're heating it, but there is no more magnesium. So no more magnesium oxide being formed. Simple. Magnesium has finished. Khatam ho gaya. That's it. Okay. So that's when we know, when all the magnesium has reacted, no more magnesium oxide being formed. And so we know that the reaction has completed. And so we can stop the experiment, right? Now, many different people should carry this experiment out, and the results should be compared. See, in the beginning of this, they are saying that several different groups in a class can prepare magnesium oxide by heating a coil of magnesium in a crucible. So why several different groups in a class? Do you know why? Why are we using several different groups in a class to carry this experiment out? Yes, Zainab? Yes? Yes?
Yes, if there are many groups doing the same experiment at the same time, and if the result comes the same, then you can guarantee that the experiment is going correctly. So if majority of the students have a different answer and someone has different answer, then something could be wrong.
Right, right. And then, you know, we have to, they will all be like, like as many times I mean, the more times you carry out an experiment, you are reducing the errors. You are reducing the errors. So when different people will be performing the same experiment, meaning, you know, like you are reducing errors. And so if one person is making an error, the other group can compensate for that, right? And so overall, we have an accurate result, right? So now this you understood how we got the mass of magnesium, subtract the mass of, so now what am I, after we have performed this experiment, now we will find out, I mean, we already know the mass of magnesium, and we will find out the mass of magnesium oxide, and now we will see the ratio. What is the ratio? Okay, so mass of magnesium would be the difference between this value and this value, which is this, and then the mass of magnesium oxide is the difference between these two values, which is this. So then the mass of oxygen that combined with magnesium was this. And I hope you understood how they calculated the mass of oxygen, right? They subtracted the mass of magnesium from the mass of magnesium oxide. You know, it's just like 2 plus 4 will give us 6. Okay. So if I don't know this, I can just simply subtract 2 from 6 to get 4, right? So same. Mass of magnesium oxide minus the mass of magnesium will give you the mass of oxygen that reacted with it, right? So what are the results? The results are plotted in the form of a graph, okay? The x-axis is the mass of magnesium, the y-axis is the mass of oxygen. And you can see that though there are few variations and deviations, the overall result is a straight line passing through the origin, which means that the ratio of the mass of magnesium and the mass of oxygen is constant. It's the same, okay? That means the same mass of magnesium reacted with the same mass of oxygen, right? So what is the conclusion of this experiment? The more the magnesium used, the more the oxygen combined with it from the air, and the more magnesium oxide is produced. And the graph is a straight line. Okay, so the ratio, so that means a definite compound is formed by a chemical reaction, right? Now, can we calculate the percentages of their masses? Can we calculate the percentages of their masses? Right, let me see. Okay, this. So the percentage of magnesium in the final product, 0.36 grams was the mass of magnesium, 0.24 grams was the mass of oxygen. Add them together and you will get 0.6 grams of magnesium oxide. That means in this 0.6 grams of magnesium oxide, 0.36 grams is contributed by magnesium, 0.24 grams is contributed by oxygen. So now can we find out the percentage of magnesium? So percentage of magnesium would be mass of magnesium divided by the total mass of the compound, which is 0.6 grams. Mass of magnesium divided by the mass of the whole compound, which is 0.6 grams, multiplied by 100, you get 60%. And how do I calculate the percentage of oxygen in the final product? Mass of oxygen divided by the mass, again, of the whole compound, which is 0.6 multiplied by 100, and I get 40%, right? Right. So now the percentage of magnesium to oxygen would stay the same in all the compounds. Okay, no matter what the source of the compound might be. Okay. Okay, which shows that they're in a fixed ratio. Okay, with similar experiments. Okay. So this is this. Now let's, do you guys have any question? And then I will do this question 6.4 on page 157. Amna, I can see your hand raised. Yes?
Miss, what are those small squares in the graph 6.6 represent?
6.6. What do these squares represent?
Yeah.
Yeah. Okay, yes. Mass, a graph of the results obtained. So results obtained from heating magnesium in air. The graph shows the mass of oxygen that reacts with various masses of magnesium. Okay, like for example, like we will have different values for the masses of oxygen. Okay, we will have different values for the masses of oxygen, and then we will plot it against the different masses of magnesium that it reacted with. Okay, so basically this block is the common point. Okay, so mass of oxygen against the mass of magnesium. So this much oxygen reacted with this much magnesium. Yeah, these are the results, you know, for performing experiments and calculating values each time. Okay, so they plotted this mass of oxygen and mass of mass of magnesium, these two values. So this is the x-axis, this is y-axis. Okay. Yes, Atika. Is it clear, Amna? Yes, Atika. Yes, Atika. Did I unmute you? Yes, Atika, now you're unmuted.
Yes, ma'am. Yes, ma'am, your video is coming very blur.
My video is blur? Okay. Okay. Now let's start this. Do you have your own book? Do you have your own book? Okay. No, that's okay now. Okay, let's do this question 6.4. A class of students carry out an experiment heating magnesium in a crucible as described on page 155. The table shows the results of the experiments from the different groups in the class. Okay. So what will be, you have to fill in these boxes. Write down the correct mass of oxygen that reacts with the magnesium in the last 4 experiments. So I told you, how do we calculate the mass of oxygen? By subtracting magnesium from the mass of magnesium oxide, right? So 0.1 minus 0.06 will give you this. And so how will you get these values? By subtracting the mass of magnesium from the mass of magnesium oxide. Subtract the mass of magnesium from the mass of magnesium oxide and you will get these values. Okay. But the, okay. Okay. Plot a graph of the mass of oxygen reacted against the mass of magnesium used. Draw in the line of best fit for these points. Now you have to draw a graph. Okay, comment on what this graph line shows about the composition of magnesium oxide. So anybody wants to discuss the answer to these two parts, B and C? What do you think the graph would look like based upon what we just read, what we just learned? What do you think the graph would look like? Okay, Amazur Rahman. Yes.
Ma'am, the graph would be in a straight line.
Very good. Passing through the origin, right?
Yes, ma'am.
Yes. So what, okay, let me ask Maruj. Let me, yes, Maruj, I'm unmuting you. You're not getting unmuted. Okay, Huda Chishti.
It will have a fixed ratio of oxygen
And magnesium, right?
Yes.
Straight line shows that the same, the ratio between magnesium and oxygen is the same, no matter what masses we use. Okay, so this was easy. Okay, now let me introduce you to the concept of mole. What is a mole? Okay, let's talk about what a mole is. Now, mole, don't be confused. It's not that hard. Mole is just an easy way to count the number of atoms. Okay, it's just an easy way to count the number of atoms. Now, what do I mean by that? You know, we all know how small atoms are, right? Now, if I tell somebody that, okay, put 1,600,000 and then 500,000 grains of salt in this curry. Do you think it's possible for that person to follow my instructions? I mean, how on earth will he count 1 million tiny grains of salt? It's not possible, right? So he would say, you know, like, talk in easy terms, you know, talk in easy language with me. And then if I say, okay, add 2 tablespoons of salt, so that would be easier. Okay, so aise kaho na, right? So similarly in chemistry, because we're dealing with such tiny particles, atoms, we had to have, you know, a unit like a tablespoon. Okay, something that we can easily measure, and each time we measure it, it should be precise. Now, if a person knows exactly how many grains come in 1 tablespoon, it would be even more precise. So we know that, okay, in 1 tablespoon, 1 million grains are there. So it would be easy. 2 tablespoons meaning 2 millions. 3 tablespoons meaning 3 million. So I can easily add, subtract. It's easier for me. Okay, provided I know how many grams, how many grains there are in 1 tablespoon, right? So you can think of this mole as a tablespoon for chemists. They came up with this concept of mole. So instead of the exact number of atoms, they just use mole, provided they know how many number of atoms are there in 1 mole. So for example, this is my mole, like sort of a, You can think of it as a ball or a bowl, and it always has these many atoms or molecules or ions or whatever you're talking about, okay? If you're talking about ions, they should be 6.02 into 10 to the power 23 ions. If you're talking about atoms, they should be 6.02 into 10 to the power 23 atoms. And if you're talking about molecules, they should be 6.02 into 10 to the power 23 molecules. So whatever particle you're talking about, that depends upon your substance. If your substance is a metal, you'll be talking about atoms. If your substance is a simple molecule, like carbon dioxide, you will be talking about molecules, right? And if you're talking about, for example, an ionic salt, then you will be talking about ions or formula units, okay? So this is called an Avogadro constant after the scientists who came up with this concept, okay? This is called Avogadro constant. This is behind, after that scientist. And the symbol to this is given capital L. The symbol is capital L. Right? Now, so now you understand what 1 mole is. 1 mole is nothing but just a unit to make our calculations easy. 1 mole is always going to have these number of particles, okay? Be it atoms, molecules, or ions. Now, when I was talking about the relative atomic mass, which is mentioned in the periodic tables, I told you that the unit is atomic mass unit. Mass of 1 atom is given in atomic mass unit. Whereas when you talk about mass of 1 mole, when you talk about the mass of 1 mole, it is the same mass, numerically, same mass, but the unit is now grams. Why? Because remember, why did we have this unit? Because this 1 atomic mass unit was equal to, 1 atomic mass unit was equal to this. 1 atomic mass unit was equal to 1.66 into 10 to the power minus 24 grams. So that this was a very awkward number. And so scientists gave this simple atomic mass unit to keep things easy, right? But now we are talking about these many particles. So it's easier now to use grams. Now it's easier to use grams because 1 mole has these many particles. So when you add up all of their mass in atomic mass units, I mean, it's easier. And so we use the units grams. Now we can easily use the unit grams. So remember, molar mass is the same as the mass of 1 atom, but the unit would be grams. Okay, now you might have a lot of questions or confusions, but don't get confused. You can read into this in detail. Why is it that that numerically the values are the same? The reason why the numerically the values of 1 atom and 1 mole is of any substance is the same is because of the definition of atomic mass unit. Okay, 1/12 of the mass of carbon-12. Okay. And you can go into the details if you want. Okay. Now, in molar calculations, they usually ask you to calculate the number of moles. They give you the total mass and they ask you the number of moles, or they will give you the number of moles and ask you the mass, or they will give you the mass as well as the number of moles, and then they will ask you to find out the mass of 1 mole, the molar mass. Okay, now how to go about it? Now I made this analogy. Well, I didn't have time. I wanted to fill this with sweets. Okay, for example, this is a bottle jar full of sweets and candies. Okay, this is my analogy. I didn't get time to make sweets. Okay, so this is jar full of sweets. Okay, it's full of sweets. Now, is it, it would be very time consuming and difficult for me to take out each sweet and weigh it separately, right? It would be, and so I don't know how many sweets there are in. There are lots and lots of sweets, and it would be difficult for me to calculate or to count the number of sweets individually, or to even weigh them individually, right? So what is an easier way? What do the industries do? What do the factories do? Remember, many of the packets of sweets, they have labels on them and they mention how many sweets there are. So do you think they take out and they count each and every sweet and then write down the number on the label? No. How they do it? They know the mass of one sweet or one candy. They know the mass of one sweet, right? They weigh the whole bottle. Okay, that is the total mass of all the sweets, and I am neglecting the mass of the bottle. Okay, forget the mass of the bottle. So once you know the mass of the whole thing and the mass of the candy sweet, it's easy to find out the number of sweets or the candies inside. How? You divide this mass by the mass of one sweet, and you will get the number of sweets. Easy. That's how they do it. That's how even the banks count the coins. They know the mass of one coin. They will weigh the whole pile of coins. They divide the mass of the pile by the mass of one coin, and they know how many coins there are in the pile. So that's how they count the number of coins. Similarly, we can have the mass of the whole thing, the whole substance, divide that by the mass of one mole, which we can easily find out from the periodic table, and that will give us the number of moles, right? And we can look at this formula another way. If, for example, we want to find the mass of the whole thing, then if we know the mass of one sweet and we know the number of sweets, easy. Mass of one sweet multiplied by the number of sweets, we can calculate the mass of the whole thing, right? Similarly, we can calculate the mass of one sweet if we divide the mass of whole thing by the number of sweets. So it's the same formula, and we are playing with it, and we can use it in different ways to find out different things, right? So just molar mass is equal to the relative formula mass in grams. So this formula that I just explained you is shown here on page 159, this triangle. Okay, so this is that triangle where, you know, you keep the thumb rule. So if you want to find out the molar mass, you hide the molar mass, so mass divided by the number of moles. If you want to find out the number of moles, you hide the number of moles and you divide mass by the molar mass. And if you want to find out mass, then multiply number of moles by the molar mass. But remember, don't just memorize it. Try to understand it. So it would be easier. I never memorized this formula. This is how I look at it. This is how I look at it. So if they want me to find out the mass of one mole, I know how to, you know, I'll divide the whole thing by the number of moles and so on and so forth, right? So even if you forget the formula, you will never go wrong. Now, let's try a few questions. Let's try this question on page 165. On page 165, 6.7. Copper 2 oxide can be reduced to copper metal by heating it in a steam of hydrogen gas. Dry copper 2 oxide was placed in a tube which had previously been weighed empty. The tube was reweighed containing, so this is again tearing. Okay, first they weighed the test tube alone, empty, and then they weighed it again containing copper 2 oxide. The difference between the two would give you the mass of copper 2 oxide, and then set up as in diagram, right? Hydrogen was passed through the tube for 15 seconds before the escaping gas was lit. Okay, the tube was heated for a few minutes. The apparatus was then allowed to cool with hydrogen still passing through. The tube was reweighed at the end. At the end of the reaction, the tube was weighed again. The process was repeated until there was no further change in mass. See how they keep repeating until they wait for the mass to be constant. Why? Because that shows that the reaction has completed. Right. Now, part 1, where is the most suitable place to clamp the tube? Where is the most suitable place to clamp the tube? Also, remember to explain your answer. Yes, Muhammad Abdul Rahman.
Near the cork, ma'am. And it will melt and expand from the bottom.
Very good. So, so what is your reason for clamping near the mouth or around the neck or near the clamp?
Because at the bottom it will expand.
Right. So if we have clamped at the bottom, the test tube might crack or break, right?
Yeah.
Yes, good
Yeah.
job. Okay, part 2. Why was the hydrogen passed through for 15 seconds before the gas was lit? Why was the hydrogen passed through 15 seconds before? Yes. Okay, Huda Chishti.
So that
Yes.
the air would be so that the air could be removed.
Yeah, air could be removed out and then also giving some time for the reaction to take place, right? Yes.
Yes.
Okay. To remove the oxygen. Why do we want to remove the oxygen? I mean, why do we want to remove the air? So that why do we want to remove the air? Sayyid Nabil. Yes, Sayyid Nabil. Yes, Nabil. I'm unmuting you. Okay. Okay. Amina. Okay.
Because we need pure copper.
Yes, yes, because we don't want any reaction with air. We want reaction with hydrogen, right? And what is the reaction going on? Yes, what is the reaction going on? What's going on in this? Can you write the word equation or a symbol equation? Can anybody give me orally the word equation or symbol equation for this reaction? What's going on in here? Zainab Wasim. Yes, Zainab?
For word equation, it could be copper plus hydrogen.
Copper?
Is equal,
Copper?
yeah,
Is this copper? Or is this copper?
copper to oxide.
Right.
Sorry,
It's
copper to
reacting with?
oxide is reacting with hydrogen.
Right. Copper to hydroxide. And I hope you know how to write formula because this is copper to oxide. So this is +2 -2. Get
Yes, Miss
cancelled.
Sonu.
Yeah, so we just simply write CuO plus hydrogen. Give us what? What will be the products?
Copper hydroxide.
Copper hydroxide. Are you sure?
I don't know, Miss.
Oh, okay, that's okay. Okay, Abdul Rafi. Abdul Rafi, I unmuted you. You want to tell me the products of this reaction?
Copper plus water.
Yes. So basically what's going on? What type of a reaction is this? What type of reaction is this? Right, very good. Yes, okay. Sundus gave me the answer. Saad, you tell me.
Redox reaction, miss.
Very good. Redox reaction. So what is getting reduced and what is getting oxidized?
Oxidized, the hydrogen is getting oxidized and the copper is getting reduced.
Very good. Because here oxidation state is +2. Here the oxidation state is 0. So oxidation state is decreasing. So this is reduction. And here the oxidation state of hydrogen is 0, whereas here it's +1. So this is oxidation, right? So this is a redox reaction, right? Where hydrogen is acting as a reducing agent, right? And copper oxide is acting as an oxidizing agent. Okay. Why was it necessary to repeat the process until there was no further change in mass? This we have already discussed. Okay, Maruj. Yes, Maruj?
Just to confirm that the process is completed.
Yeah, the reaction is complete. Right, right. Good job.
Yeah.
Yes, yes. Because when all the copper oxide will have been reduced, there will be no more copper oxide getting reduced, and so the product mass will stop changing, and so the final product mass will be constant, right? Okay, the results for the experiment are given below. Okay, what are these results? The mass of empty tube is this, the mass of 2 plus copper 2 oxide is this, and so then what would be the mass of copper 2 oxide? So you will subtract 46.12 from 47.72, you will get the mass of copper 2 oxide. And then at the end of the reaction, they are weighing the mass of tube and copper again. And so mass of copper would be, again, this 47.40 minus 46.12, because you want to cancel out the mass of tube. So mass of oxygen in the copper 2 oxide, how did we get the mass of oxygen? How did we get the mass of oxygen in the copper 2 oxide? So I will keep this equation with me. So we calculated the mass of copper. We weighed the mass of copper 2 oxide to be 1.6 grams, and mass of copper was 1.28 grams. Okay, and then mass of oxygen in the copper 2 oxide. Okay, how did we calculate the mass of oxygen in copper 2 oxide? How did we do this? I forgot. The mass of oxygen in the copper 2 oxide. How did we do this? Do you remember? Okay, I totally forgot. Does anybody know? Does anybody remember this? Mass of oxygen in the copper 2 oxide. Oh, okay. Okay, yeah. Okay, you can subtract 1.6 from 1.28, right? This, no, sorry. 1.6 minus 1.28 will give you, does anybody have a, can you subtract this? 1.28. 10 minus 2, 10 minus 8 is 2, 5 minus 2 is 3, and 0.32. Yeah, okay, 0.32 grams. So that's how we get the mass of oxygen. So what did I do? This is what I did. Copper oxide minus copper would give me oxygen. Is it making sense? Copper oxide, I know the mass of copper oxide, I know the mass of copper. The difference will give me the mass of oxygen. Okay, so mass of oxygen is this. Okay. Now, copy out and complete the results table above. Okay, that we have already done. How many moles of copper atoms are involved in the reaction? Now, if we want to find out the number of moles of copper, so what are they asking us to do? Remember that analogy, I will use that analogy, this thing. So what information do we have? We know the mass of copper, right? How many moles of copper atoms? So I know the mass of copper was this. So I know the mass of the whole thing. So remember, I know the mass of whole thing, which is 1.28 in my case. Okay. Do I know the mass of 1 mole? Yes, I can find out from the periodic table. Mass of copper from the periodic table is 64, right? So 1.28 is the mass of the whole thing, and mass of 1 mole is 64. So I can find out the number of moles of copper, right? And what is that? I need a calculator. Can you get me one? Okay, who has calculated? If anybody has calculator, please calculate it for me. Yes, Atika, I'm unmuting you. Did you divide 1.28
yes,
by
miss.
64?
Yes, the answer is 1 over 50 or 0.02 grams.
0.02 moles. Remember, these are number of moles.
Okay.
Right. So the answer is 0.02 moles. Thank you very much. Jazakallahu khairan, Atika. Okay, let's move on. So did you understand how I did this? Did you understand? So I'm using the same thing, same analogy. So the mass of the whole thing I got from here, from these tables. Mass of copper produced was 1.28. So I divided that by the mass of 1 mole of copper, which numerically is the same as this, 64 in grams. So a 1.28 divided by 64, I got 0.02 moles. That's the number of moles of copper. Jazakallahu khairan. Now let's move on to part 2. Part 3. How many moles of oxygen atoms are involved in the reaction? How many moles of oxygen atom? Okay. Oxygen, mass of oxygen was 0.32, right? So again, same thing, mass of oxygen, I will write it here now, 0.32 divided by the mass of 1 mole of oxygen from the periodic table. The mass of 1 mole of oxygen is numerically the same as the mass of 1 atom, which is 16. So 0.32 divided by 16 gives me what? 0.32 divided by 16 is 0.02. Okay, 0.02. Now also appreciate that the number of moles of copper is the same as the number of moles of oxygen. Why? Because you can see that they are 1:1 ratio in the formula. 1:1 ratio in the formula, right? So number of moles of copper will be equal to the number of moles of oxygen. Okay. Now 4. From the results of the experiment, how many moles of oxygen atoms have combined with 1 mole of copper atom? So yeah, same thing, 1:1. How many moles of oxygen atoms have combined with 1 mole of copper atom? So only 1 mole of oxygen has combined with 1 mole of copper atom. Okay, I hope you guys understood this. Now, part 5. From the results of the experiment, what is the formula of copper to oxide? Now, from the results of the experiment, so we know that the ratio between copper and oxygen is 1:1. Therefore, copper is 1 and oxygen is 1, and we don't write 1. So this is the formula. This is the formula of copper oxide from the experiment, right? Now write a word equation for the reaction, and then using the calculated formula for copper 2 oxide, write a full balanced equation for the reaction with hydrogen. So we have already written this equation. It is this equation, and I think it is balanced. 1 copper atom here on the left side, 1 copper on the right side, 1 oxygen on the left side, 1 oxygen on the right side, 2 hydrogen on the left side, and 2 hydrogen on the right side. What will be the state symbols? This is, Sundas, you tell me the state symbols. Solid, hydrogen is gas, copper is solid, water is, yeah, in this case it's gas in the form of vapors because we are heating, right? So alhamdulillah, we have introduced the concept of mole and did that experiment. Is there any question? Please ask. Yes, Ahmad, you want to ask? Yes. Yes. Okay, I cannot hear you. Atika, I can see your hand raised. Do you have a question? Okay, I cannot hear you. Okay. Okay. With this, I will end this class. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.